Right. Hello, everyone. Good morning, good afternoon. I'm personally in Vancouver, British Columbia today, just presented at another conference, and I was thrilled to speak at Data Bash. My presentation today is about table formats, especially in the data lakehouse. So the who, what, and why of data lakehouse table formats. And this has been coming up a lot, so I think there will be some good questions. And go through some of the intricacies between the different options that you have. And just a little bit of my background. Feel free to connect with me on LinkedIn. That's where I'm most active and respond to messages. Professionally, right now I'm an evangelist at Dremio, a data lakehouse company. And I focus specifically on data analytics and on artificial intelligence. And travel around the world speaking with external audiences, developers about how data lakehouses can enable unified analytics, semantic layers, AI. Before that, my previous life, I was a leader of lots of different AI and analytics programs in higher education and financial services. I was a VP of analytics at JP Morgan, Senior Director of Analytics and AI at Arizona State University, and a bunch of other places. On the side, I teach graduate programs in data analytics and data science. It's the joy of and highlight of my week. I engage with a ton of students. At any moment, I have between 50 and 150 students. So they keep me on my toes and ask me good questions. So these presentations are helpful for me so that I can answer their questions. And just a quick overview of what is Dremio. This is definitely not a sales presentation, but I get a lot of questions about, like, what is Dremio? Before you talk about table formats, what the heck is Dremio? Dremio is a query engine that works on data lakehouses. It also does lakehouse management. So it works with one of the table formats, Apache Iceberg particularly, but it also can work with, for instance, like Delta Lake. And a bunch of people use Dremio. As a freebie for you, we did write the definitive guide to Apache Iceberg with O'Reilly. And so if you'd like a free copy of that, scan the QR code and get a digital copy. If you buy it on Amazon, it's $60. So I recommend don't buy it. Just get a free copy of it, and we're happy to provide that. We just signed another contract with O'Reilly. We'll have another exciting book coming out probably next year. The development cycle on that is about a year long, but a related topic and incredibly applicable. But yeah, please get a free copy of the definitive guide to Apache Iceberg. It takes you all the way from the beginning, like what is, some of the concepts we'll touch on today. What is a data lake? What's a table format? All the way up to how do you use Spark within Iceberg. All right, well, let's kick off. So talking about table formats for the data lakehouse, we got to start at the very beginning. What is a data lake? So going back to the very beginning, we've got the database, the data warehouse, and both of them have storage, table formats, catalogs, processing, and then databases are typically row-based, and data warehouses are typically columnar. And these have been the backbone of a lot of our storage systems in almost every industry for years and years. But they really only deal with structured data. And so there are some limitations. While there are a lot of efficiencies in databases, there's definitely some limitations there. You can't scale compute and storage separately. You need to increase them at the same time. Data warehouses, which typically hold the gold layer or application layer of our data, all the data sets that analysts and data science are pulling in order to feed their models or their dashboards, go through typically the data warehouse. But now we're making copies along the way. It can get expensive. Even though they're in the cloud, compute can be expensive and potentially inefficient. So we end up making extracts and things. So there's definitely trade-offs. So then we started with the data lake. And the data lake really answered the question, well, we don't just have structured data. We've got all this semi-structured and unstructured data. How are we going to store that? And Hadoop was really kind of the first object storage that came out on the market. And Hadoop was a big answer for everyone. So it really begged the question, like, wouldn't it be nice just to have a copy of data that anyone could access, where multiple tools could just work out of the same data instead of having it spread all over the place, different databases, different warehouses, but have it efficiently? So that's really when we started moving towards the data lake. And so the idea is, how about we just store the data as files, and then we can use different tools to work with those files. And so we came out with Hadoop, which was basically a system to take a bunch of computers and treat them as one large storage layer with a whole ecosystem of tools. So there was Hive, Pig, Impala, lots of things. A lot of it's still around. Hadoop grew like crazy. There's a lot of companies modernizing off of Hadoop, but Hadoop for a long time was really the standard of how you were going to work with object storage. And so that's really the storage structure. So essentially, you store the data as a bunch of Parquet files with structured analytical data sets. You could store images, basically anything you can put inside of Hadoop. But the problem was that maybe, for instance, these Parquet files really make up a table. Maybe instead of just seeing them as individual files, they're really a table. But there's no way to automatically know that those individual files inside of Hadoop are a table. So the Hadoop system, or an object storage system like S3 or ADLS, they don't magically know that these files are a table or that these files are another table. So the management of the object storage is a big challenge. So what the system knows, it just knows that these files are stored and that they're there and where they are. And so this really limited the ability of tools to interact with the storage layer, because they don't necessarily have the metadata understanding, the context of the data on the storage layer in order to access it efficiently and intelligently. If you provided access to this Hadoop storage layer to a data analyst, there's really not much they can do with it. They're not able to work with the unstructured text file or semi-structured text files, the Parquet files. They needed that extra ETL process of moving it into a warehouse. So while storage could potentially be cheap, it wasn't useful. Some data scientists were able to get in and work directly on the object storage layer. But for the most part, most business cases and application level cases were not able to use Hadoop directly. There had to be another level. And so that limitation caused a lot of companies to start investigating, like, what else can we do to maybe make more use of our storage level, of this object storage. And so the data lake paradigm was often used for ad hoc querying, but it is so limited. And so the dream of having one copy of the data that could work with multiple tools was still out there. This is where we started moving towards the data lakehouse. So what the heck's a data lakehouse? And so it's an architectural pattern. And so your storage is still in a data lake, and the architectural pattern on top of it makes it a data lakehouse. And there's a few things that go into that. It provides structure, performance, flexibility, scalability, a unified platform, and cost effectiveness. And let's look at how it can do that. So when we look at the data lake, let's break it down into different components. What do we have? We have the storage layer. We have compute and processing, so it's deconstructed, right? On the data lake, storage is separate from compute. And that's one of the main things that makes it easier, is that you can swap out your different engines and your storage. There's lots of tools like AWS Athena, Dremio, which can help with that, Trino. But it's not quite, it doesn't have all those benefits that a data warehouse had. Remember when we looked at a database versus a data warehouse, while can be expensive, it really was so easy to use. I mean, data warehouses are amazing for data analytics and getting that gold level where you can just plug a bunch of tools into it. But again, expensive. We've made a bunch of copies of the data along the way in order to get that ETL into that state. So if we could just have the data accessible in our data lake, so then we get the cost effectiveness, but also the ability to have application level and quality data there where a lot of tools could access it. That's the dream, and that's what the data lakehouse is trying to accomplish. And so that's really what makes up the data lake, is those two components. So data lakehouse with this architectural pattern comes in. They have the storage and the compute, but add in a table format, which we'll talk about, and then a catalog to interact with the table format. So a way to identify things as tables and somehow being able to collect and understand that the tables exist. That's what was missing from a data lake in order to make it accessible and useful for downstream consumers. So when we add that in there, you now have all the functionality of a warehouse, and it's in this flexible, agile, decoupled modular structure. It's deconstructed, so you really can swap out storage, table format, catalog, processing, and query engine. And so this architectural pattern is what a data lakehouse is, with the end goal of being able to provide that data warehouse capability directly on top of the data lake. Yeah, happy to see that my title is it's trippy there, so I apologize for that. So if you're looking at it in practical terms, you have these data sources. You ingest them in to your data lake. And because you're using a table format, which we'll go over, which provides all the metadata for all those data files. Remember, we looked at Hadoop as tons of Parquet files and images and text files. So we're ingesting those type of files into our data lake. And we've got the metadata, we've got a catalog, which is going to track for us which tables exist, which files roll up to which tables. And we can use tools like Dremio, Snowflake, Apache Flink, Apache Spark, Upsolver. They can all begin working with that system. They can all begin accessing through that table format the underlying data in those tables. So the table format is really the key to enabling us to have one copy of the data on the data lake and treat it as an application layer. So the data lakehouse architecture is particularly suited for AI workloads and unified analytics. But I'm seeing it a lot in AI right now because, traditional AI, of course, with deep learning, and AI is not just the model, right? We talk about in generative AI a lot, how many billions of parameters was this foundational model tuned on, trained on, and then tuned. But it also needs to be the quality of the data. Companies that are building their own generative AI models have to have quality data underneath in order to build a model that's going to understand the context of their business. If they have a RAG model or a graph RAG model, which can provide a little more of that context, the underlying data has to be good. It doesn't magically know It doesn't like an AI model doesn't magically fix poor data quality. And also training these models, the best is if you can have a 360 view of your business. Well, what does that require? It requires integrating data from all kinds of different sources: SQL Server, ADLS, MongoDB, Cassandra, ERP systems like SAP, Salesforce data. Well, how do you get that in there? Let's get it in the data lake and then use a table format to create a unified layer, and then the AI training can read from there. So even if you need to go further downstream and move it into Elasticsearch or into a vector DB like Pinecone, at least you've got a unified layer where everything is in one spot, rather than trying to ingest directly into the vector DB. You're now getting it all into the data lake, getting it unified and organized so that the AI model can then do its work. Not only that, moving into the data lake, the process there, which we'll talk a little bit about, is incredibly powerful and fast, and there's different table formats which you can choose depending on your priorities. But companies like Uber and Facebook have already adopted Lakehouse architecture, and they have reported significant improvements to their capabilities. So we talked about how the table format is really the key to enabling the data lake to have these abilities similar to a data warehouse. And there's really three main options for a table format. And let's look at those. So as we dive a little bit deeper, to appreciate this, let's talk a bit about the fundamental unit when we talk about the data lake, which is the file, which we alluded to earlier. When it comes to analytics, a standard way to store structured data is in a Apache Parquet file. And the Apache Parquet file improves upon the formats of CSV and JSON. Parquet files are awesome. And when you use something like a CSV or JSON, there's a couple different problems. One, they're text files, which means you're using text encoding, which takes up more space for the same content. Two, especially with CSV files, they're inherently row-based. So basically, if you want to do something like get an aggregate analysis off your data, like, hey, what's the total of all my sales? You would need to read every row when all you really want is the total column. So you want to be able to add up the total of each sale instead of reading every row. So they can be pretty inefficient. And as data grows, which is growing, it's growing incredibly. I saw a Gartner chart 3 days ago about the potential amount of data that they're projecting that's being stored, and it's exponentially higher than last year. So just hundreds of exabytes of data is being stored. And if we're trying to do analytics, especially aggregate analytics on top of that, which, let's be honest, we typically are, if we're doing metrics, KPIs, a lot of that's just aggregated data. We can't have row level, like we just can't. We can't read an entire table in order to provide an aggregate number. That's what leads to insanely slow analytics, or having to do a large extract to launch it into Tableau or Power BI. And now if you've got an extract feeding your dashboards, it's no longer live, and you're storing it twice again. So there's lots of challenges there with having the row-based storage. So a Parquet file helps fix these problems. One, it's binary format, so it can store that same information from that CSV file in a much smaller space that's specifically engineered for the structure and purposes of analytics. Two, it structures the data as columns, so as a columnar format. See that 10 times twice, columnar? I say it a lot, and sometimes I still have problems with it. So instead of having groups of rows, you have groups of columns. And so that column for total sales in our example would essentially be a separate data structure that I could just pull individually. I wouldn't need to read all the rest of the rows in that file in order to generate that aggregate number. But you may not necessarily need that particular column for every record. So it helps you really prune down and have efficient queries if you're using Apache Parquet. So to make it more efficient to scan, you have groups of rows, and what they do is they take those columns, groups of columns, and break them into chunks of rows. So each row group is made up of the columns for those rows. And the beauty of this is that each row group has a footer with metadata about that row group. And metadata is really the key. So imagine saying, hey, this row group contains all users between the age of 20 and 30, and this row group has users between 31 and 40. And this allows the query engines like Dremio, Trino to do what's called predicate pushdown. So instead of scanning the whole file, it can say, okay, based on the data in the footer, do I need to scan this row group at all? Or I can skip these row groups based on the metadata and scan more efficiently. Because it's columnar, I can only grab the columns that I need. So overall, it allows for much faster data loading and data processing because it can load the data faster. Because I only load the data that I need from that entire file instead of loading the entire file. Then I can process the data very quickly. And because it's columnar, it can be quickly converted into memory formats like Apache Arrow, open source, which is incredibly fast for processing in memory. And so if we've got something bigger than that, if we've got data sets that are bigger than just a single Parquet file, when the Parquet file is really good, while the Parquet file is really good at doing analytics, but what happens is your data sets grow, and we all experience that. And so you might have a situation when your user's table might be, in this case, 3 Parquet files, and each Parquet file has different row groups. In this case, I want to describe to whatever tool I'm using that these 3 files really are a single table. They roll up into a single table, and that's how I want to treat them. If I do that manually, it leads to all sorts of potential problems. So what happens when one of my analysts accidentally says that only user 1 and user 2 Parquet files as a table, but they forget to include user 3? You will have inconsistent data sets, analytics won't be right. There isn't an absolute way of defining that in the table. So when you have multiple Parquet files that make up one data set, you really don't want the users to define these rules around the data set because the files, they don't understand one another. They need something else to help organize that. They're not aware of one another. Each one's a unique file containing a piece of data, and we need some sort of glue to treat them as a bundle. And so that's the challenge of, we have multiple files. They really are a data set. There's nothing inherent that's making them aware of each other. There's nothing inherent that makes it very obvious that these should go together. And so manual manipulation of these is incredibly inconsistent. And this is where the table format comes in. So the original table format was called Hive, and Hive metastores are still around. Before, there were things like Apache Iceberg and Delta Lake and Apache Hudi, which we'll go more over in a little bit. There was Hive. And so just a little history about Hive. Hive was created because you had all this data in Hadoop. Remember our original object store? And you had to use a tool called MapReduce to run analytics on it. Shout out to all our MapReduce folks, if you remember that. That's when I was entering analytics, is when, probably at the peak of Hadoop and Hive and MapReduce and Pig and all these tools. When I first got into data, I was like, I have to learn Pig. Like, what is going on? I don't even understand this. And then I got into it, and it started to make more sense. But it was very manual and burdensome, to be honest. And MapReduce required you to use a framework in Java to write an analytics job. So you'd have to write this Java code that would define the data set and say, hey, here's the files that equal this data set. And then these are the operations I want to do on it. And this is all written in Java. So most analysts, most data engineers, they don't write Java, but you really had to if you were a data engineer, if you were working with Hive. So even if you know Java, it really isn't the easiest way to write a basic analytics query. So people wanted to do the things the way they're used to. That's SQL. SQL, love it or hate it, which I personally love it, is the common language of data. We use Python. Yes, we do use JavaScript and some Java out there, but the vast majority of data operations are going to be in SQL. So being able to use that common language of SQL would make things easier for everyone. Data analysts know SQL, data scientists know SQL, data engineers clearly know SQL. So people really wanted to use SQL in order to do some of these operations. Hive was created to make this process easier. So if you would say, hey, give us the SQL and we'll translate it into a MapReduce job. And that's really how Hive worked. So Hive was taking the SQL query, translating it into MapReduce. Other formats and frameworks did come along later. There was Tez, which could supplant that. But the idea was that Hive would translate to something initially. It was translating into MapReduce. But to do SQL, you need to know where the table is. There has to be a way to understand it. And just based on the name of the table, what's inside the table? That's the key. You need to be able to say, here's the table name, and something needs to understand what files roll up into that table. So the paradigm Hive used was a folder. And there's a folder called user. And the files in that folder are the user table in this example. And so that did work. It helped us get organized. This became the way that we could recognize what's in the table. It's whatever is in the file, whatever's in the file, the data inside the file made up the table. And so this allowed us to write SQL, and it made asking basic questions a lot easier. Could you imagine telling your data analysts today that they need to write Java in order to get their analytical query done? It just wasn't happening. It wouldn't happen today. And so the problem is that the work that the query engine has to do in this Hive structure is that the way we define the table is so simple, but we don't know how many files are inside that folder. So the user folder. I think I misspoke earlier. I was saying the files in the files. The files in the folder. And so there's not a lot of info about, hey, what's inside here, approximately what's the size, all of those things. So we know that the folder's a table. Everything in there rolls up to a table. But now the engine has to do file listing operations. Whatever you're using to query it has to do file listing operations. It has to bring up a list of every file in the table and then individually read each one. And then every time you open and close a file, that's work the computer has to do. And the more work it's doing, the longer it takes to execute a query. It might not need to read all those files, but it's going to if they're in that folder. So you might have to read 1,000 files when you really only needed 30 of them to really get the info from the query that you're trying to do. So it wasn't ideal, but it was better than what we had before. And it was also really hard to do granular updates because generally you would track the tables through something called the Hive Metastore, and the Hive Metastore would track, hey, this folder is the users table, but it would also track partitions. And partitions, in this case, were treated like little subtables inside that table. And so it would say, hey, here's this users folder, and these folders are the partitions within that table, but it wouldn't track the individual files. So it stopped at the partition level. And if you ever wanted to update just one record, like CDC, you would have to update the entire partition folder. So that could be a much more expensive and time-consuming operation. You had a very limited table evolution. If I wanted to add a column, I would potentially have to rewrite every data file and rewrite the whole table. If I wanted to change anything about the table works, how it's partitioned, the schema, and so on, it would really require rebuilding it. And all these challenges made it difficult to do the same type of work that you would do inside a data warehouse. And so the data lake was still not to the point where you could use it to the same extent as the data warehouse because of all these challenges that we just talked about with Hadoop and Hive. So there's a modern approach to table formats, and this is what it's trying to solve. Companies, Netflix, Facebook, they're dealing with all of these challenges. They're dealing with giant amounts of data, and they wanted to be able to access it efficiently on their data lake. They wanted to be able to do analytics on the data lake. And with Hadoop and Hive, it didn't make it easy enough to make the data lake your source for analytics. So this new generation of table formats began to arise. They work more like this. So essentially, you have a group of files. We're still talking about the groups of files that make up a table. And instead of saying, hey, the table is the files in a folder, the way Hadoop did, it says more, hey, we're going to have this metadata off to the side. And the metadata will tell you which files are in a table. And it doesn't matter where they're physically located. The metadata tells you, hey, users1.parquet, user2.parquet. Even if there's 300 files in the folder, that there are or aren't part of the table. So only the files defined in the metadata will make up that part of the table. Makes it super efficient. So what's the schema of the table? It's what the metadata says. Even if the files are missing a column or have an additional column, we can apply the schema defined in the metadata so that the query engine creates the output after reading the files. It's always going to conform to the schema, which is incredibly helpful. It also makes it possible to change the schema. The same thing applies to partitioning. And we talked about how in Hadoop and Hive that you're doing almost subfolders when you're creating partitioning. And so when we do partitioning in a modern table format, it's really saying, hey, this file and that file are partitioned in this certain way. And we're aware of it because the metadata is allowing us all sorts of flexibility with how the data is managed. By having all this metadata, I can do a lot of the figuring out that I'd have to do by opening each file individually. Don't have to do that. We can do it by reading the metadata. And so I can have a handful of files and get a lot of work done. An analogy I like to use when it comes to the metadata is to imagine a kitchen. If I go to my kitchen, there's a bunch of drawers and cabinets. And if I were to look for one thing, like one fork, and I don't know where the forks are, I might have to open every cupboard, every drawer to try to find it. And that's going to take a while. But if I had a clipboard with a list of every item in the kitchen and their location, I could save myself a ton of time by just grabbing the clipboard and saying, hey, where's the forks? Oh, it's here. Let me go straight there and grab the fork. And that's what the metadata is. It's like an index, a separate structure that tells you about the thing that you want to look for so that it makes it easier and faster to find it. And so the metadata-centered approach defines much more than what we just had with the folder in the Hadoop paradigm. But what the individual files that the data's in, you're able to fix a lot of the the associated problems of the Hive format, making it easier. So for instance, features will include ACID transactions and the different table formats we're going to talk about. So ensuring data consistency and reliability, which again, crucial for AI and analytics. Schema evolution, allowing changes to the data without breaking queries. This flexibility is essential for AI analytics when the data requirements are often changing. Hidden partitioning, optimizing data organization for faster queries without complicating the data model. And this can significantly speed up analytics, make it very fast if you do efficient and effective partitioning. Sometimes I'll meet with companies and their queries are running slow, and we'll look at how it's partitioned, and that's the problem. So there's a balance to it of having just enough partitions, but not too many partitions. And then another benefit is time travel and rollback, allowing you access to historical versions of the data, which is really crucial for reproducibility. So these are the benefits that modern table formats are bringing to the table. So Apache Iceberg is the first table format that we'll look at. Apache Iceberg comes from Netflix. The creators of Apache Iceberg created it at Netflix and then open sourced it. And so Apache Iceberg, how that works. So the query engine, if you're going to run a query through Apache Iceberg, here's how this would work. The query engine is going to run down and consult the catalog. The catalog is going to, remember we talked about the clipboard with the metadata. The metadata file has information on the different manifest lists, and the manifest lists have information on the different manifests, and then the manifests ultimately know the files in the storage. And so having this cascading query path allows for the query planning to really prune off a lot of things that aren't needed. You don't have to read rows and files and columns that aren't required to fulfill the query. And so as you go down, the metadata file is read for partitioning, schema, location of the manifest list for the desired snapshot. Manifest list is used to do partition pruning and identify the manifest with relevant files, and then the manifest is used to do the min-max filter, prune individual files, and the remaining files are scanned for the query. And so the query planning, it may even take just a couple seconds longer. The actual total query execution is insanely fast with Apache Iceberg. In the Apache Iceberg architecture, the metadata files are stored as JSON. Just like we talked about, the metadata files are the high-level definitional table data, really helps determine what is where should the query begin to look. The manifest lists are Avro, the file that lists all the manifests, and then the manifests themselves, again, Avro, files that contain the lists of the files with their table level statistics. So Apache Iceberg is growing in popularity quite a bit. We recently saw Databricks purchasing Tabular a few months ago, and Tabular was the company founded by the creators of Apache Iceberg. And so Databricks, who created Delta Lake, which we'll talk about in just a second, is also now working with Apache Iceberg. And so there was a while where companies were really wanting the benefits of having this open table format and being able to do analytics and AI directly on the data lake. But because there's multiple table formats, Iceberg and Delta Lake, for instance, there's Hudi, but we'll talk about that. They didn't know which to choose. They didn't want to make the wrong decision. It's kind of like when in the video era, when there were two main DVD formats and people didn't want to buy the wrong DVD player because they didn't want it to become obsolete. They didn't want to buy Blu-ray if Blu-ray wasn't going to be around for a long time. So that was the mindset and challenge for a lot of companies for a few years. But with the acquisition of Tabular by Databricks, a lot of companies are much more comfortable moving into Apache Iceberg. It's open. There's a million. There's not actually a million, so I guess I shouldn't say that. There's a ton of different contributors from companies like Apple, Amazon, Dremio, lots of Apache Iceberg contributors, all working to make this the table format that's most efficient and effective for everyone. And that's the beauty of open source. And so the catalog is really going to be the source. When you're reading Iceberg tables, they need to roll up into a catalog, and the catalog is what you connect the query engine to. So the catalog is the key. And like we talked about earlier, it's modular. You can really swap in one Iceberg catalog for another Iceberg catalog, totally fine. You can swap out Dremio for another query engine. It really makes it very easy to just swap in and out, which is a huge benefit. And so another open table format is Apache Hudi, which comes from Uber. So if you think about Uber, with the type of data that they have a ton of streaming data. Their data is moving super fast at a very high quantity. And that's where Apache Hudi comes in. So Apache Hudi is really great at being able to identify streaming data and transactional data. And so Apache Hudi is used by companies where high quantities of streaming data need to be accessible and queried quickly. So Apache Hudi really thrives in that environment. And then the way Hudi is formatted, let's say we have our sales folder, and we've got our data files inside of our sales folder. Then we've got our log files associated with each data file. And so Hudi really relies on the transaction log, and it's going to be able to help us query our transactional data much more quickly. And so Hudi is really the table format for real-time, quick processing and querying of transactional data. And the way it does this is by reading those logs. So if we're looking at the timeline, it's got all these commits and compaction, rollback, but that's what it's reading. And so Hudi, when you query it, is really looking at those log files in order to get to the data that you want quickly. And so the way that it's structured, you've got partition folders, base data files, and log files that all describe the changes to the base files. And so this is really what helps it move quickly by focusing on those transactional logs. I'm looking at time. I want to make sure that we have enough time to get through the other table formats as well. So a Hudi query would look like this. So it would set a timestamp to query the table it's based on. Based on the timestamp, determine which files are part of that table and which logs should be should the changes applied from. Use file stats, column state, and bloom filters in the metadata folder to prune the files. So that pruning's key. Pruning's really what makes things go faster. And then scan the files that weren't pruned to execute the query. So those log files are key and what sets Hudi apart. We also have Delta Lake, which comes from Databricks. So the way that Delta Lake is structured, if we're looking at the same thing, we've got our sales table, and it's made up of all these data files. Delta is really great with working with Spark. And the way they do this is that they have their what they call their checkpoints on their logs. And so Delta is able to use the checkpoints in order to query efficiently. And so the checkpoints really help organize the logs, and the logs help you understand which files should or shouldn't be included in the query. And so Delta Lake is another fantastic table format created by Databricks. And if you exclusively use Databricks, then you likely already use Delta Lake. Delta Lake isn't necessarily super interoperable with other tools, but if you're only using Databricks, then that's not a concern for you. And the Delta architecture, as we just talked about, right? We've got the overall file, the table. It's going to have that checkpoint file, which helps group them, which goes down to the logs, and then the logs help us understand which underlying data needs to be queried. And so similar to with Hudi, this is how a query would be performed. You build the current file list based on the existing checkpoints. Once the checkpoints are exhausted, continue with the log files, use the stats collected to prune the file list, and then scan the files that were not pruned to execute the query. So you're seeing a pattern here that it's very similar to, for instance, Hudi, but a slightly different methodology. And so all of them, when we're looking at what do they accomplish, all of them give us those ACID transactions, which is critical in order to have trustworthy data accessible for analysts and end users to query, just like a data warehouse would provide. So boom, we get all of that with all three table formats. With table evolution, all of them do schema evolution, which is fantastic. With partition evolution, currently only Iceberg is providing partition evolution, but you never know with the development cycle that may come to Apache Hudi and Delta Lake. But right now it's Apache Iceberg, so if partition evolution at a large scale is important, then Iceberg's likely the way to go. With row level updates like merge on read, so Iceberg has merge on read, and with position deletes and equality deletes, and there's a really cool way that Iceberg handles that with the delete files. Hudi does it with merge on read that uses log files, and then Delta will use what they call deletion vectors. I'm much more familiar with Iceberg and how it does the merge on read and deletes. It creates a little delete file that the system will then later read and execute. So it's incredibly fast. So that's why it's really great for schema and partition evolution. In terms of Lakehouse versioning, catalog versioning, right now, I was just looking at the Delta Lake Unity catalog. I still don't think it has catalog and table versioning. The Apache Iceberg catalog that provides all the versioning is Nessie, which is another open source project that you can use with Apache Iceberg. But again, you can swap in any compatible catalog or query engine to work with your Iceberg or Hudi or Delta Lake tables. It just has to be compatible, and you can swap it in and out. For instance, with Iceberg, you could use Nessie, like I talked about, which has those kind of Git-like versioning features where you can branch and merge and do all of those awesome things with your data. You could use Polaris, which Snowflake has contributed to Apache. I think it's still incubating at this point, but lots of contributors to that. AWS, Snowflake, Dremio's contributing to that. In fact, intends to merge Nessie with Polaris if that commit will be approved in the future. That's the thing with open source. You don't 100% know if it'll be approved, but that is the intention, is to kind of merge those catalogs together. Unity catalog with Delta Lake is awesome. If you're using Delta Lake, Unity is an incredible catalog, which is really great to work with, and the interoperability is coming. We recently saw an interview with Ryan Blue, and then who is the creator of Apache Iceberg, who now also works at Databricks due to the acquisition of Tabular, and then also the creator of Delta Lake, who also works at Databricks. And they were talking about how interoperability is key, because you don't want to have to stress and think too hard about what is my table format. You really want to abstract a lot of that away from the end user and just have it work. You just want the end user to know, hey, here's my query, and I'm going to run it, and I don't really care where the underlying data is or how it's structured or what the table format is. I just want it to work, and I want it to be super fast and correct. And so interoperability among these different table formats and catalogs will be critical here going forward. And I think that's the vision from those creators and from the open source contributors. In terms of partitioning, right now Iceberg has the upper hand on partitioning. So as we talked about, like, Iceberg is best for evolving schemas, evolving partitions at a huge, super efficient scale. Because if you think about Netflix, who was the first use case for Iceberg, that's really the type of data that they were dealing with. Hudi doesn't need to do that. They're dealing with transactional data. And then Delta Lake does need to do that, but the capability isn't quite there yet. So in terms of interoperability, so that's the nice thing with being able to have this data lakehouse structure, is that you can swap in, as I've said, probably too many times, you can swap in different components that work with each other and put the control in the power of the user. You can swap in and out query engines as long as they're compatible with the catalog and the table format. You could swap in and out catalogs. If you're on in Iceberg, if you're on Nessie one day and you want to switch to Polaris, you can. Both of those are open source, so you really have a lot of power. You can do a proprietary catalog like Glue, AWS Glue. You can do the Dremio catalog. It's your data, and as long as there's lots of components that are interoperable, you're going to be able to pick and choose the best components for you to create your own data lakehouse pattern. So Apache Xtable, also incubating right now, is working to convert the metadata between the formats and try to make like a crosswalk. So that's exciting to be able to read and write and talk between the different formats. And using Delta Lake Uniform to write to Delta and sync to Apache Iceberg and Hudi metadata is something that's coming. So right now, a lot of catalogs can read from Delta, but they can't write to Delta. So at least there's that. So at least if you had, for instance, a bunch of data in Databricks, and you had a bunch of data in ADLS in Iceberg format, so you've got both Delta Lake and Iceberg, at least you would be able to get a consolidated uniform view by reading from both formats. So there is that, and more is planned and coming. And so the Data Lakehouse catalog, which we touched on, and I don't want to drill too far into this, but the Lakehouse catalog is really organizing the metadata. I really wish that they had probably chosen a different name for it instead of catalog, because it's not like an enterprise data catalog. It's really a metadata catalog, which just says where the metadata is, because it's comparing it to an enterprise catalog like Calibra or Informatica has a catalog. Well, any of these enterprise-wide catalogs, it's not the same thing. So then if you have a metadata catalog for your table format, it does not replace the need to have a enterprise data catalog. So the role of, in Iceberg at least, the role of the catalog is really to connect your Iceberg tables to the query engine. So the query engine hits the catalog, and think of the catalog like the source. It has all the metadata. It knows where all the tables are through that query plan that we just looked at. And then it goes down and gets the data. So you could swap these catalogs. You've got Nessie, you've got Tabular, you've got the Dremio catalog, you've got Glue. With the query engine, you could swap those out. You've got Flink, Spark, Dremio, whatever. It doesn't matter. They are interoperable. And so that's really, really exciting. I know we're at time, but with thinking about the table format, I hope that this gives you a good overview of, what are table formats? What's the benefit of a data lakehouse? Why are people talking about it? Well, it's to get that all of the data warehouse capabilities inside the data lake so that you can really minimize the amount of ETL that you have to do, that you can have open tools that you can swap in and out and make it modular, more agile, and then have a uniform view that you can then use for downstream use cases like uniform analytics, building a semantic layer, doing AI across all your data, building a customer 360 without having to move it into a warehouse and pay to hold the data twice, increasing your compute and storage costs, sometimes dramatically. And so that's the purpose of the data lakehouse. Be super fast, be super efficient, be cost effective, and give you access to your tables and data very quickly, but then also give you the power to swap in and out the components that are best for you and for your use case.